At its core, the dot product takes two vectors, let's call them A and B, and compares them. Instead of spitting out another vector, it boils their relationship down into a single elegant number known as a scalar. So what does this number actually tell us? It is all about direction. If the vectors are pointing in roughly the same direction, the dot product is positive. If they are exactly perpendicular, forming a perfect 90-degree angle, the result drops to exactly 0. And if they are pointing away from each other, well, you guessed it, the number is negative. Why do we care? Well, imagine you are writing a code for an enemy AI in stealth game. How does a guard actually know if the player is in their field of view? You don't need complex trigonometry. You just take the vector of the guard's forward direction and second vector pointing from the guard to player. Calculate the dot product. If the result is positive, the player is somewhere in front of the guard. If it's negative, the player is safely behind them. It is simple, computationally cheap, and incredibly effective. But the dot product doesn't stop at AI. Let's look at computer graphics. To figure out how bright the surface should be, the rendering engine calculates the dot product between the surface normal vector, the invisible line pointing straight up from the geometry, and the light vector. The closer those vectors align, the higher the dot product and the brighter that specific pixel becomes. This single calculation is the absolute foundation of 3D lighting. And finally, think about movement physics. Your player is standing on a slope. How does the physics engine know if they should stand still or start sliding down? By taking the dot product of the slope's normal vector and the world's absolute up vector, you instantly know the exact steepness of the incline. Compare that scalar to your friction threshold and your player starts sliding. Unlike the dot product, which gives you a single number, crossing vector A and vector B gives you a brand new third vector. The magic of this third vector is that it is completely perpendicular to both of the original vectors. If you want to visualize this, just hold up your right hand. Point your index finger forward to represent vector A and point your middle finger out to the side for vector B. Now stick your thumb straight up. Your thumb represents the resulting cross product. It is a trick called the right-hand rule, and it is an absolute lifesaver when debugging 3D math. So where do we actually use this? First, think about 3D models. Everything in a game is built out of flat triangles or polygons. But how does the graphics engine know which side is the front and which way the surface is actually facing? It is simple. The engine takes two edges of the triangle, treats them as vectors, and calculates the cross product. The result is the surface normal, a vector pointing straight out of the front of the polygon, telling the engine how to render it and bounce light of it. But it is also essential for physics, specifically torque and rotation. Imagine a car taking a sharp turn and flipping over, or even just pushing open a heavy door. To figure out the exact axis that an object is going to spin around, the physics engine takes the vector of the distance from the pivot point and crosses it with the vector of the force being applied. The resulting cross product is the exact invisible axle that your object will rotate around. Finally, let's look at player movement and cameras. Say you are programming a custom first-person camera. You know your forward vector, the direction the player is looking. You also know the world's up vector. But if the player presses the D key to strafe right, how do you know which way right actually is? You just calculate the cross product of the forward vector and the up vector, and you instantly have your right vector, allowing your player to cleanly strafe side to side. A matrix is essentially a grid of numbers, but do not let the spreadsheet look fool you. In a 3D engine, a matrix acts as a master transformation machine. How does it actually work? It starts with matrix vector multiplication. Think of this as feeding a single 3D point, a vector, into our machine. The math engine takes your vectors x, y, and z coordinates, runs them through the rows and columns of the matrix, multiplying and adding the values together. What pops out on the other side is a brand new vector, and your point has been successfully moved to a new location. Think about every single object in a game world. A rock, tree, your player character. Every object has three basic physical properties: translation, which is a position, rotation, and scale. We call this TRS. Instead of calculating these three things separately and wasting performance, a game engine bakes all of that data into a single 4x4 matrix. When you want to move an object, just run a matrix vector multiplication on its structural points, and the entire 3D model snaps into its new state instantly. That brings us to pure matrix multiplication, multiplying one matrix by another matrix. This is not just about moving a single point anymore. This is about combining entire transformation machines into one mega machine. This is absolutely crucial when dealing with coordinate spaces. Imagine a character holding a sword. In the sword's own little isolated bubble, what we call local space, its center position is just 0, 0, 0, right at the handle. But where is that sword in the massive overall game map? To figure that out, we use matrix multiplication. By multiplying the sword's local matrix by the character's world matrix, we chain them together. That single operation bakes both sets of transformations into one, instantly converting the sword's local coordinates into world space. That is exactly why when your character runs, swings, or falls, the sword stays perfectly glued to their hand. And that will be all for today. If you want to see some applications of these principles, check out this video where I talk exactly about matrices, especially one master matrix controlling 3D graphics rendering. Thanks for watching. If you like what you saw and want to see more in the future, click the subscribe button. Ciao!